Hello, good evening, everyone. My name is Al-Meqdad. Welcome to my presentation about Introduction to Probability. Today I'm going to talk about the PDF, probability density function. The probability density function PDF, or density of a continuous random variable, is a function that describes the relative likelihood for this random variable to take on a given value. The PDF is most commonly associated with absolutely continuous univariate distributions, and for the random variable to fall within a particular region is given by the integral of this variable's density over the region in the illustration, giving alongside the probability density for the median to fall within the limits of Q1 and Q2 is given by the darker shaded area. The darker shaded area, as we can see here, imagine we're having a probability for rain. What is the probability that the rain is exactly 2 inches? If we say the probability of the rain is exactly 2 inches, it's going to be 0. There's no area. Like when we say this is 2, the integral of it to get the probability. Here in the PDF, the probability equals the integral of the area. So the area under the graph is exactly 1 unit, equals exactly 1 unit. So the probability also equals 1 unit. The probability equals the area. The law of the PDF, Flex equals probability of x being bigger or equal a, less or equal b, equals or the same as the integral of Flex dx going from a to b. If you get the question we explained here and before, region for x like from 1 to 3, then it's a continuous random variable, and we use the PDF law to solve it. The question I'm talking about is the rain. How many inches? If we say here 2, exactly 2, there's nothing, there's no exactly 2. The probability of exactly 2 inches is 0. There's no area, there's nothing, it's 0. But if we take an interval like from 1 to 3, this area is going to be 25%. This area is going to be 25% as well. The left side and the right side are equal in size, both of them equal in size. This can't be bigger, the right side can't be bigger than the left, or the left can't be bigger than the right. This is the PDF. So from 1 to 3 is we're going to take the interval of this period to get the probability of the rain being between 1 inch and 3 inches. The PDF is a Flex which describes the shape of the distribution. It can take uniform, exponential, or normal distribution, which we'll talk about later in this video. Now let's talk about the cumulative distribution function. The cumulative distribution function, CDF, is the probability that the variable takes a value less than or equal to x. That is Flex equal probability of bigger x or capital X being less than or equal x. It equals a number. For a continuous distribution, this can be expressed mathematically as Flex equal the integral from minus infinity to x FLU dlu. For a discrete distribution, the CDF can be expressed as Flex equals sigma x from x to I equals FLI, 0 FLI. These functions are used to calculate the area under the curve to left from a point of interest. So imagine there is a point N. We're going to calculate the area under the curve from N all the way to the left from here. And if we have like 2 points, like another point right here, it's M. We're going to take the difference between M and N. Imagine it's 0.2. So if M was like 0.7, N was like 0.5, this would be like 0.2. It's the difference between those two numbers. So if we take N, it's going to be from N to 0, like we said above, area under the curve. Evaluate the accumulated probability for continuous probability equals area under the curve. Since the maximum probability is 1, the total area under the curve will be 1 as well. So the area under the curve like this is also 1. First rule we must know, it must not be decreasing. So it must like go up, up, up and stay up, or just might go just up, 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 and you just stay on the same line. Not decreasing. It's not a decreasing function, or not a decreasing distribution. The limit of the CDF x getting close to minus infinity must equal 0. The limit of CDF x getting close to plus or positive infinity must equal 1, exactly 1. If those three rules were applied to this drawing, we can see it's still increasing, it's not decreasing. We can still see the limit of x when x getting close to negative infinity, it's 0. And we can see that x when limit of x when x is getting close to positive infinity is exactly 1. Not bigger, not lesser, it's 1. So when to know if it's a CDF or not, we must apply all these three rules to make sure if it's a CDF or not. Now let's talk about the continuous distribution. There are three types of continuous distribution: normal distribution, exponential distribution, and gamma distribution. The normal distribution, also known as Gaussian distribution, it's always symmetrical about the m, or the median. The m is like the middle point, or as we call it, the median sometimes. The left side and the right side are equals. They are both the same size from in the normal distribution. Small note: the normal distribution is a continuous distribution. M is the same as mod, on the same as median. So if we can call it mu, we can call it mod, we can call it median, or we can put just a number like 0 most likely. The total area under the curve is equal to 1 unit. The probability equals the area under the curve. So as we know, the probability equals 1. So the area under the curve, of course, will equal 1 unit. BDF is represented by the normal distribution graph, which we will show in the next slide. As we can see here in this graph, it looks like the BDF, probability density function, where the left side and the right side are both equal the same. And there's a point. It's a 0 here. And sometimes we call it mu, sometimes we give it a number. It's a 0. This represents the normal distribution. As we can see, the median here, or the m, there is a number 0. If we take plus 1 to the right or minus 1 to the left, we can see the size of these two areas are the same, which is 34% both together equals 68%. The x-axis represents the variable. For an example, take the height. 1 for people who are 170 centimeters, minus 1 is for people who are 150 centimeters, and between those two, 0 people who are 160 centimeters. As we can see, we want between 170 and 150 centimeters. We can't just take like what's the probability of people being 150 centimeters? It will be 0, as we talked about earlier, because there's no area. The y-axis represents the probability density function, Flex, which gives the height of the curve at a point x. The next thing I'm going to talk about is the gamma distribution. The mathematical definition of the gamma distribution is y is distributed as gamma with parameters alpha and beta, which we will refer as a and b, if it has a corresponding BDF. Probability for y, given that a and b, alpha and beta, equals beta on gamma between two parameters n by y to the power of a minus 1, alpha minus 1, to the by a to the power of minus beta y. Y is bigger or equal 0. A and b are bigger than 0. Y can equal 0, but a, alpha, and beta can never equal 0. As we can see in this gamma distribution graph, here we're going to show the gamma distribution graph and the effects of alpha, the effects of changing the alpha. Normally, the gamma distribution graph looks like the black line would look like this. It's like an exponential distribution. Would look like this. It peaks at 0 and go further down to 0. So if you look at this, if you look at this, alpha at the black line equals 1, alpha at the red line equals 2, alpha at the green line equals 3. What we can know from this, each time we increase the alpha, the peaks go less down and goes to the right. It goes less down and goes to the right. The peak goes less down, goes to the right. And the y increases. The other two drawing where alpha equals 2 and 3, you can see that when we change alpha, it starts from 0. Then the peak goes to the right a little bit. Each time you increase alpha. When you increase alpha, you also increase y according to the law. Y to the power of alpha minus 1. In e to the power of minus by. Here also the e decreases. The y increases, the e decreases, because when the value of the y is bigger, the e decrease each time. Gamma distribution graph and effects of beta. This time we're going to talk about the effects of beta. With beta, it's much different. Increasing beta has some huge effects. The height of the distribution changes a lot. The distribution itself decreases. Simply saying, the graph is going to become taller and sharper, and it's going to reach 0 after the maximum much bigger. As we can see here, it starts from 0, going up fast at the top, like at the top of the distribution, and then going down faster and going to 0 much quicker than the other drawings. Here, as you can see, it's tall peak. It's a taller drawing, much sharper, and it's going to reach 0 after the maximum much quicker. The exponential distribution. How long do we need to wait before a person visits our website? This question involves time. We took something from before involving time as well, which is called the Poisson distribution, which is how many times does an event occurs in a period of time. Let's say that every 25 minutes a person visits our website. So every 25 minutes, we shall have a person who visits our website. But what about the time between each 25 minutes? This interval where no one visits our website is a continuous interval which is given by the exponential distribution. So the interval in which, like, imagine having a website. People visit you, people click on the website every 25 minutes. From 0 to 25, this period of time where no one clicks, this is the exponential. This is continuous interval which is given by the exponential distribution or ruled by the exponential distribution. As we explained before, the exponential distribution is the interval between two periods of time where no one shows up. Lambda is the rate in the Poisson distribution, but in exponential distribution, it's mu, which is equal 1 on lambda. So if lambda equals 2, mu will equals half. Some of the laws of the exponential distribution, fx equals 1 on mu, hit by e to the power of 1 on mu in x. So this is an example of the exponential distribution. As we can see, the black drawing, it's going like the gamma distribution from up to down. Peaks at 0, high in the air and down. As we increase the y or changes the y, the graph itself changes because y is connected to mu, because mu equals 1 on y. So every time we increase y, mu will be less. So every time we change y, lambda, mu will be less. So if it's a half, mu will be 2. If it's 1, mu will be 1. If it's 2, mu will be half. The drawing, as you can see, it's going like this. The biggest one where lambda is 4 and mu will be a quarter, 1 on 4. It's going to peak at like 1 and then going down fast to 0. The smaller lambda is, the much slower it will take the graph or the drawing to reach 0. As you can see in the red line, it's going like this. It's not touching, it's still not touching the x-axis, or still not touching the 0 axis. And the black line is the same, but as we see the blue line and the green line are going faster, are going to reach faster to zero. After the maximum, they are going to reach faster to zero.